Hey guys, so I decided that I was going to try to make a couple, go through a couple problems so that you would understand what's going on. And so if you look at this, this one, I don't have it written down, but this is number 37 on basically page 125, I believe is what it's on. And so this first question goes, how many electrons would it take to equal the mass of a proton? So basically, what we're going to go is we have mass of one proton equals basically the mass of one electron, right? And we know that protons weigh more than electrons, so how many of those are we going to have? So this is the basic way that you set it up. Now, if you look on page 104, you'll realize that on there's a table, it's 4.1, that gives you all the masses of the subatomic particles. So how you would end up solving this is you would divide by the mass of this one electron on both sides, and then you'd set it up like that. So X equals the mass of one electron over the mass, I messed up there, of one proton over the mass of one electron. And so then you would just plug in what you already know from the table, which is 1.67262 times 10 to the negative 27 kilograms over 0.00091 times 10 to the negative 27 kilograms. And that would give you the final answer of 1.8 times 10 to the 3. And that's how many electrons you would need to equal the mass of one proton. And that, of course, is the significant figure of 2 from the 91. So this is how this works. I'm going to kind of go through it. If at any time you need to pause it, you can go through and actually pause it. So now let's look at the mass of a proton that's required to neutralize the charge of 1 gram of electrons. And this is number 40 on page 125. Well, first I want you guys to point out that this guy is what's important. The problem I just showed you, and on the page that is page number 104, it's in kilograms, right? And so what we need to do at this point is we need to convert. So I'm going to show you how to convert really quick if you don't remember. And this is something that you need to learn how to do because you'll be doing it all semester long if you haven't figured it out. Well, let's start with the proton. And we know that its mass is 1.67262 times 10 to the negative 27 kilograms. Well, what do we want? We want grams. And so how you remember, if you remember how to convert, you're going to go, okay, how can I get grams over here and get rid of kilograms here? And you could do that by putting kilograms on the bottom, grams on the top. This would mark out and you have this left. Well, 1 kilogram equals 1,000 grams, and multiplying this out, you'd end up getting 1.67262 times 10 to the negative 24. So you would do this as well with the electrons. Now, if we're trying to find the mass of proton that's required to neutralize the charge of 1 gram of electrons, well, we want to first start out, okay, we have 1 gram of electrons, right? And so basically when we're figuring this out, we're going to say that if we have, for every 1 proton, we're going to have 1 electron. Now, these guys weigh differently, and that's what we're looking at, right? So when we talk about its weight, And basically our end over here is going to be in grams, right? We want to get rid of electron. So how we do that is basically if you have one electron here and we're trying to get mass, right? And so we have, when we convert this to grams, we have 9.1 times 10 to the negative 28 grams for one electron. Now, if we look here, we have a proton, and we want to figure out how much one proton weighs. Well, one proton here, right, is going to be from what we got before, 167262 times 10 to the negative 24 grams. And then basically this cancels out, this cancels out, the grams down here, and you're left with 1 grams on top. And when you multiply all of this out, you get 1.8 times 10 to the 3 grams. So this is how you basically set up and utilize problems to figure out the mass or how many of electrons or protons that you would need for any given example. So this next one that we're going to go, let me go to page 49. This is 129. And this is, give me 1 second here, and I'm going to pull up a periodic table. So as we go through this, I don't know where that came from. And this is a pretty nice periodic table. It's a dynamic one. It changes. So let's go here and look at this very first one. Let's figure out what we can do. So we have the symbol AU and 79. So if you go through here, we're looking for AU and we're looking for 79. So you're going to come over here. And if you do this, you're going to realize that this is gold, right? And that when we're looking at this, you'll notice that that one number on the top, right? This is gold, right? And then this is the atomic symbol and the atomic number is at the top. If you remember, the atomic number is the number of protons, and indirectly, because everything on the periodic table is neutral, it will tell you indirectly the number of electrons. So this is the first one, right? Now let's go back to our periodic table so that we can look for tin. Now on here, oops. You'll notice it's not telling me the symbol or the atomic number. And this one's a little weird. It is, you can look, and how you can start trying to figure out where things are is, you know that it's tin, so it's a metal. We're not going to find it anywhere over here in these green, right? Or even in this area right here where metalloids are. And so if you look, you'll notice it's right here. So on here you have what is known as the, and this is a really cool thing. It pulls up all the information. So it's SN is the atomic symbol and the atomic number is 50, as 50 protons. And then copper, and this one's easier. You can go look, number 29. You can see that right there, and it's Cu. So you should be able to easily go through this and find, especially the commonly known ones, and be able to utilize the periodic table to find different things. And this is number 49, page 125. Now this next one we're going to go through, and what we're going to look, this is number 51. And as we go through here, we are going to identify if it's a metal, a non-metal, or a metalloid. So you should be able to look at this periodic table and identify different areas. As you can see, they show you here that these guys are the alkalines, the alkaline earth metals here. Here, you're looking at the transitional metals. Here, post-transitional metals here, metalloids. Non-metals are these green. Noble gases are over here. And so those are all, and they're basically showing you the difference between metals and non-metals. And these guys are metalloids here. So this is kind of a helpful thing. So SR is the very first one. And if you go through, you just kind of go through and you're like, okay, where is SR? Can we find SR in here? Where is SR? Sure. And if you look, it is right over here. So this guy, if you look, it's an alkaline earth, and you can see up here, it's telling you those guys are within the metal category. So this first one is a metal. The next one we have is, Mg, magnesium. And if you look at here, you can see it's right here. And again, this guy falls into the metals. F, fluorine. So if you look, fluorine is going to be where? Hopefully you found it over here in the nonmetals. And so this is an example of a nonmetal. Nitrogen, right there, again, nonmetal. Arsenic, right here, right? And that's what's considered a metalloid. So you should be able to use the periodic table and know where all of these are located. So you will need to memorize the general groups and how they're classified. You don't have to memorize the atomic symbols and all that. That you just look and utilize, but you should know where all these different like alkaline earth metal alkalines are and how they're put together on here. So number 53, we're going to go and we're going to talk which elements do you expect to lose an electron in chemical changes. So this is number 53, page 126. And just to let you know, when we're talking about losing an electron, right, that will give you an idea, though we haven't talked about it yet when we approach this section. But now that we've talked about like chemical bonds and things of that nature, you should realize that generally what happens is a metal and a nonmetal comes together in a chemical bond. And so what's interesting about this is if you remember that the metals and nonmetals form ionic bonds and that the metal actually gives up its electrons to the nonmetal, so something like potassium chloride. This is the nonmetal, this is the metal, and he will end up getting his so that he becomes positive and he is negative. That can give you a really, really good hint about which of these guys are going to actually lose an electron. It would be all the metals that are in here. So, for instance, potassium would lose an electron. Barium would lose an electron. And copper would lose an electron. Sulfur and fluorine would not. Now we're on number 67. And basically what we're going to do here is in 67, we're looking at which pair is most similar. So let's kind of look at these guys in the periodic table. Let me make this a little bit smaller so that we can have this kind of down here while we go through these. So we put that there, we put that up here, and let's kind of take a look at these. So the very first one we're going to look at is silicon and phosphorus. So that is A. The next one, fluorine and chlorine. That's B. A. Sodium and magnesium. This is C. We have 10 here, and we have molybdenum over here. That is D. And this is what I would suggest that you guys do when you get these kind of questions. Don't just look at it and go, oh, I'm going to figure this out. Let's actually go to your periodic table and figure out what things are. And so that is D right there, the green one that I have. And so I can tell you right off the bat, if they're far away from each other on this, then they're definitely not going to be similar. So this one and this one, you can mark those out. This one and this one, you can mark those out. And then we can start looking at the ones that are next door to each other. Well, if you look at this, for instance, let's just look over here. This is the easiest one to tell versus this one over here. You can already see that when we look down, these guys, right? These are our groups. So we have a group of alkali metals, and then we have the alkali metals and alkaline earth metals. Well, we classify them that because these guys in these groups that go down, they are similar. So these guys are actually in different groups. So they're not going to behave close to each other. But if you look at this guy right over here, you'll notice these are in the same group going down. So essentially, the chlorine and the fluorine in this answer would be the elements. They come from the same group. They would be the most similar because they have similar chemical and physical properties. Get out of this. So yeah, this part, as you could probably already see, we're using the periodic table a lot, and that's a big part of this one. So now we're on number 71, and we want to fill this in. So let's go. I'm going to push this down over here to be able to kind of see it, and let's move this up a little bit, and then we can fill this out. So let's go. So the very first one is K. So you're going to look around and you're going to notice K is over here. So let me click on, well, we can't click on this because I'm in here. So the group number that it is, right, is going to be up at the top. And it's either here, and a lot of times you'll see either 1 or you may see 1A up there. Now the group name, as you can see, because we're here, right, is this. So it's an alkali metal. And this is considered a metal. Let's go to the next one down. And so if we look, we have BR. And BR is over here. And so this guy is either going to be up here if you see, actually let me move this, is number 17, or you might see it based on, remember the valence electron that we looked at, 7A. It is a halogen. You can see that right there. And it is considered a nonmetal. So you should be able to look at this guy and be able to answer questions, simple questions like that. So now let's go to number 8 here. And so when we have these ions, and this is number 73, right? Atoms can ionize. And they ionize based on their stability state. Some of them are more likely to give up electrons. Some of them are more likely to gain them. And so when they form ions, we want to be able to figure out what they're losing in the sense of that overall kind of change. And so if you look at here, if we have sodium and he becomes an ion, right? What does that mean? Well, he is positive. Which if you are positive, it means that you had to lose a negative charge, right? And what have negative charges? Well, electrons. So in this case, it would be sodium positive plus, and we're losing an electron. Now in this case, we have oxygen, right? And he is neutral. And we're adding 2 electrons to him. So how we would write that is you would take your oxygen and you are adding 2 negative charges. So you add that to the top to basically tell everybody how many negatives you have there. And some things ionize and they give more than 1 electron away. For instance, calcium, when it ionizes, it goes into a positive 2 state. So basically, if you have 2 extra protons, right? And that means extra, you essentially are going to have 2 electrons that you have lost. So this is how you write ionization equations for atoms that are ionizing. So now we're on number 77. And we want to go and figure out how many protons and electrons we have in each ion. So let's go. We're going to use our periodic table again. And we're going to figure out what we have here. So let's find sodium. Sodium is over here. And this is where you have to figure out what we've learned from in the past. So we have an atomic number that is 11. And we have the atomic mass that is 22.99. So on here, how many protons do we have? You would have 11 protons, right? How many, if we haven't ionized yet, right? This is, let's say we are at an A here. And then we have how many electrons? In this case, just to let you know, it goes to 22. It doesn't go up to 23. It's just something you remember. So you have protons, 11, electrons, 11, right? And so in this case, when we ionize, it means that basically we have a +1. So we have 1 extra positive charge. Well, we're not going to get protons, right? We're not going to go up to 12 because if you go to 12, you are going to turn into magnesium. So what's going to happen is you are going to lose an electron. So the number of protons you have remain, right? It's going to be 11. So I'm going to write it down here. Well, 11 protons, right? And you're going to lose, we're at +1 here, right? So we're going to minus 1 electron. So that gives us down to 10 electrons. And that makes us have a positive +1 charge. So that's how you figure it out. Let's try another one. Let's go to barium. That is down here. So on here, barium has the atomic number of 56 and the atomic mass of 137.33. So if we have basic old barium and nothing has changed, he is going to have protons of 56 and electrons of 56. But what do we know? He is +2. So basically, we are not going to change our protons, right? We are going to have to lose 2 negatives, right? So basically, we have 56 protons plus, we take 56 and we minus 2, we have 54 electrons, which equals +2 charge. How is this going so far? Hopefully it's not too bad. Let's try one more. Let's try oxygen. This up a little. So oxygen is over here. And if you remember, nonmetals tend to not lose electrons. They tend to gain, or they will like to have electrons, especially oxygen. This area is very, very electronegative, right? And so what's going to happen here, if we have regular old oxygen, right? The atomic number is 8. The atomic mass is 16. So the protons we have are 8. The electrons we have are 8. So this guy, though, has what? Well, we don't do anything with our protons, right? We do stuff with our electrons. So we have 2 more negative charges, right? So this guy is going to have 8 protons plus 8 plus 2, right? 10 electrons, which will equal -2. So that's how you find or determine the number of protons and electrons in an ion. Remember, ions are just positively charged or negatively charged atoms. Now, you can predict how the ions, or predict the ions form for each element by looking at the periodic table. So let's go down here again. You're like, is this ever going to end? Hopefully, I'm hoping that it's helping you a little bit. So let's get this up a little bit, and let's go on here and let's look. So this one is number 81. And so rubidium, Rb, if you look here, you'll notice, well, how many? We look at it up here. You remember valence electrons, talking a little bit. You can look here and realize, if you don't know what that is yet, that you can figure out how many electrons that they're going to lose or gain based on essentially what group they're in. And so this group right here, group 1, the alkali metals, they tend to like to release their extra electrons they have. They're more stable when they do that. And so on here, the most commonly known type of ion that we're going to get here is an Rb+, just single. And that is because it's in the 1A group. If you realize, potassium's right above it, same group. So what do you think is going to happen? Same thing. K plus, it's in that 1A group. Now, if you look over here, we have aluminum. And if you remember, basically, aluminum is if you go 1A, 2A, then you go across the ocean to 3A. It's 13.2, but that 3 is there. So basically what he's going to do is, because he's in this 3A group, he is most likely going to lose the 3 electrons that are there. And so he will become what's known as Al3+. And that's because he's in the 3A group. So this group tends to lose 1, this group tends to lose 2, and these over here tend to lose 3. Those are the most commonly formed ions. And you can see there is a periodic table inside. I'm trying to look at what page that this guy is on. If it's here, if it's later, that talks about the ions that get formed. Give me 1 second. I'm trying to find that stupid thing. It's on page 114, and they'll show you, we looked at the positive ions, but you can also look at the negative ions, and we showed one of those being formed earlier with oxygen. So let's see where we are now. We're almost halfway through. So here we're going to go, this is number 83. And 83 is asking, are they more likely to gain or lose electrons? And so on here, the very first one we have is gallium. And you can see it's right here. And so this guy, if you remember, is most likely to be Ga3+. So he is most likely to lose 3 electrons to form that positive ion, and that's because he's in that 3A group. Lithium is over here. We've already talked about rubidium and potassium and sodium for the most part throughout this semester. And so this guy tends to be Li1 or Li positive. So he tends to lose 1 electron, and it's because he's, again, in that 1A group. Now, bromine is different because he's over here. He is a non-metal, right? And he's really close to being next to the noble gases. He's a halogen. So essentially, for these guys to be stable, they give their stuff up because they don't have a whole lot of outside electrons to begin with, or the valence electrons. We'll talk about this when we're talking about bonding. This guy, though, he only needs 1 more electron to be stable. So this guy tends to go negative, which means he tends to gain 1 electron. And that is because he is in what's called that 7A group, or that halogen group. Again, you can look at page 114 in your textbook to find that. And so number 85, you should see if you can do that on your own now that we've gone through that. And 85 is basically fill in the blank to complete the table. And they ask you for like the ions commonly formed, the number of electrons in the ion, and the number of protons in the ion. And you should easily be able to do that. And if you get it, I'm not sure if it's in the back of the book. I didn't look yet. But if it's not, you can always stop by and I can check it out to see if you have the right answer on there. So let's move to number 87. And number 87 here is talking about isotopes. And so isotopes can be found basically in between starting on page 115 and how you write them. It's right after. And so Ions have to do with losing and gaining electrons. Isotopes have to deal with differences in the number of neutrons we have. And if you remember, you can find the number of neutrons by taking the atomic mass minus the atomic number, and that gives you the neutrons. So determine the atomic number and mass for each isotope. So guys, let's look at this really quick. Go here. So you can look at, when we're going through here, sorry, I'm trying to charge this up while I'm looking. I don't know if I got the number 87. Let me get in my book here. Yeah. So let me move this down a little bit so that we can look again. Have you seen a trend? We are constantly going and using our periodic table. So the hydrogen isotope with 2 neutrons. So if you know how you write isotopes, you basically use the formula that is A, Z, X. X is the symbol. The A is the mass. And this is the atomic number. So when we look at hydrogen, so we're going to determine the atomic number, which is Z, and the mass number, which is A. And so let's look at hydrogen. It's right up here. So regular old hydrogen has the here, right? And if we were looking at the atomic mass, the mass would be 1, and the atomic number would be 1, right? And so let's see, let me write this different. I don't like this. So the atomic number is 1 and the mass is 1. So that means how many protons do we have? 1. And so you can find out how many neutrons by 1. The atomic mass minus the atomic number equals neutrons, right? So we have 1 minus 1 equals 0. But the thing is, what is it saying here? It's saying we have 2 neutrons. So when we're looking at this, what changes? Does the atomic number change? No, right? The atomic number is the number of protons. That does not change. So the atomic number, or Z, right, is 1 because that's what hydrogen is. The mass, which is A, right, is actually going to be what? Should be 2, right? Because we have 2 neutrons here. So that gives us our isotope. Let's look at our next one, which is calcium. So I'm going to give you a moment to do that. 7. And so on here, let's move this up a little bit so we have more room. Let's look for calcium. Is here, right? And so we have the atomic mass, which is 40. We have the atomic number, which is 20. So the protons we have are 20, and the neutrons we have are 20, right? And so basically, it says we have 22 extra, with 22, the calcium isotope with 22 neutrons. So basically what we're looking at here, we're going to have the Z, which if you remember again, is the atomic number, which is 20. And we are essentially looking at the isotope that has an additional 22 neutrons, right? So when we look at this, our A is going to be, because we have 20, 22, which equals 42. So if you write this, how would it look? You'd start out with the Ca here, right? And what goes on the top? The 42 and the 20. So let's move on. And let's go to number 13. And let's see how we write these. This is number 89 and 91. I've combined them together. And so on here, we're going to do an oxygen isotope. And this guy is going to have 8 neutrons. And so let's look at what we have up here. So here, oxygen is right here. We have the atomic number is 8. The mass is 16. And so protons, we have our 8. Neutrons, we have our 8, right? And so when we write this, we're going to put O because that's our shorthand symbol, right? And then we have the mass. So we have our oxygen with 8 additional neutrons. So we have 16 at the top, right? For our mass number. And then for our atomic number, we have the regular old 8. And the reason why is we have 8 neutrons, right? So you go 8 protons plus 8 neutrons equals 16. I think I wrote it wrong when I did it a second ago, and I apologize for that. Let me go back here really quick because I think I wrote, so that's how you do it. I think I wrote that you'd have 22, and I didn't mean to do that. On this guy right here, when I was talking about writing it, it's because you have 20 protons plus 22 neutrons. And so that's why you get the 42 that we were looking at the top, right? And then the 20. I apologize. I miswrote. So yeah, that's how you get your mass, by doing the neutrons plus the protons. And so on this one, let's look. Aluminum. Move it down a little. Here we go. It's right up there. So here we go, right? And so we have the atomic number, which is 13. And what is the mass number? $26.982, right? Let me see, this is number, what number are we on? Oh, sorry guys, I know I'm being a little slow here. And so let's do this. So we have aluminum here. So we have the atomic number, that is 13, right? And that gives us the number of protons. And on here, we have the atomic mass that we can round to 27. So 27 minus 13 equals 14 neutrons, right? So anyway, when it's asking you, they want you to write, so aluminum is like this, right? And then at the top, you're going to write the atomic mass. So you have the number of protons, which is 13, plus the number of neutrons. So that gives you 27. And then you keep what the atomic number is, which is 13. Let's do cobalt. Here we go. So cobalt is right here. So cobalt has the atomic number of 27. So on here, they're asking you to write it. And when they do cobalt 60, they're telling you what the actual mass is here. So here we were trying to figure it out. Here they're giving it to you. So it's CO, that's 60 here. And then you put the 27 at the bottom. And that one was much easier than some of the other ones. So basically, gist of this is just find where they are on the periodic table, right? Find out how many protons they are, and then just add that to get the mass. And that goes on the top, right? And then this goes on the bottom. And then you just put the symbol, whoops, there. And that's generally how they write isotopes. So let's determine the number of protons and neutrons in each isotope. And so here we can look at here, and we basically have this guy right here is the mass, and this is the number. So number of protons are 11, right? Because that's the Z number. Now, number of neutrons are going to be equal to the mass minus the atomic number. So the mass here is 23 minus 11, right? And that gives you 12. So now we're on some of the last few, right? We're getting towards the end, and I hope you're figuring this out. So here we have carbon-14 present within living organisms and substances derived from living organisms, is often used to establish the age of fossils and artifacts. Determine the number of protons and neutrons in a carbon-14 isotope and write its symbol in the form Az14. No! Sorry, guys. My thing just died on me, and I don't know why. Hold on. Discard. Give me 1 second to see if I can get this to work. Well, I will be back with that. My thing seems to have died, so I will be back in another set to do the last few problems.